Good morning, everyone. Thank you for inviting me in this Geology and Planetary Mapping Winter School. I will talk about two specific units on Mercury, which are faculae and hollows. And I will give you also some information about their spectral properties that can be related to their composition and physical properties. As you know, the Mercury planet was visited by the Messenger spacecraft, and this spacecraft was launched in 2004. It performed several flybys, one around the Earth, two flybys around Venus, and three flybys around Mercury before to started to orbit around Mercury. And the spacecraft orbited Mercury from 2011 to 2015. This is the payload of Messenger. It includes several instruments, but I will focus on two instruments in particular, which are the spectrometer masks, the Mercury atmospheric and surface composition spectrometer, which was able to acquire the reflectance spectra of Mercury. So it gave us information how the light is reflected by the surface of Mercury. And it operated in the visible to near infrared range from 300 to 1,500 nanometer. And then I will also talk about the data from MDIS, the camera, the Mercury and Dual Imaging System camera, which was composed by a narrow angle camera acquiring data from in 700, 800 nanometer range. And in particular, I will focus on data from the wide angle camera, which was made of 11 filters, covering the range from about 400 to 1,000 nanometer. So this on the left part of the slide, you already know this map. This is the enhanced color map of Mercury. And this was produced thanks to the data, to the MDIS data acquired during the first two flybys of Messenger. So the data was photometrically corrected, and as said by Valentina, it was applied an unsupervised technique, the principal component analysis, to this data. And the results of this analysis produced several principal components. The first two principal components were used to create this map. In fact, this is a composite image where in the red channel we have the PC2 component. The PC2 component is usually related to the slope of the spectra. And as you can observe on this right part of the slide, these are the spectra acquired by the MDIS camera in the 11 filters. And the slope are the trend of the reflectance at increasing wavelengths. So the PC2 represents the slope of the spectra. The PC1 is usually related to the albedo, the reflectance. And the third channel that composes this image is, as said by Valentina, the ratio between the first and the last channel of the MDIS data, the ratio between 430 and 1,000 nanometer. So this map allowed us to identify several spectral units, which can be distinguished by mainly differences in reflectance and spectral slope, which represent the green and red channel respectively. As you can observe from this image of the spectra, all the units have a positive spectral slope. So this means that the reflectance increases at longer wavelengths. It as a higher, progressively higher values when I move to longer wavelengths. But we called as red units those terrains that have a spectral slope with a higher slope, with a higher value with respect to the average mercury terrains. And the blue units are those with a slope that has a lower value with respect to the average one. I just briefly describe you the several terrains detected on Mercury. They are divided in major, which are more extended areas, and minor terrains, more localized areas. The major terrains are the smooth plains produced by effusive volcanism. These are divided into high reflectance red plains, such as the regions inside Caloris Basin. And this is the brightest and reddest smooth plains on Mercury. Then we have the intermediate plains, which is spectrally similar to the global means. And then we have the low blue plains, which are instead intermediate between the intermediate plains and the low reflectance material. This other major terrains is the darkest and bluest unit of Mercury, and as said by Valentina, is the early graphite bearing crust, mainly exposed by major impacts. Then we have another major terrains, which are the intermediate terrains, and these are spectrally similar to the global mean, such as intermediate plains, but they are more cratered. So they are probably older and degraded smooth plains. Then we have the minor terrains, which includes the fresh crater ejecta, and these are the ejecta characterized by high reflectance and shallow visible slope. They are probably not compositionally different from the underlying terrains, but these spectral properties are probably related to a low space weathering alteration. Then we have the red material that is also ejected material, which has instead a redder spectral slope. And then we have holos, which I will talk in detail in the next slide. And red material is part of the so-called red units, and the red units involved both red material, pyroclastic deposits, and the red pitted ground. Pyroclastic deposits and red pitted ground are the faculae. So we can say that faculae are made by a central pit, such as in this case of pyroclastic deposits. They are made by a central pit surrounded by a spectrally bright and red terrains. That is the facula. And these are formed by explosive eruption. The red pitted ground are characterized by no discernible vents, or sometimes are made by multiple pits, and they are characterized by the spectrally bright and red terrains. So I will focus on these three units, the holos and faculae, and concerning the faculae, I will mainly talk about pyroclastic deposits. Let's start with the faculae. As said before, they are characterized, in particular, the pyroclastic deposits are characterized by a rimless central pit, that is the vent of eruption that you can observe here in this image. And they are surrounded by a spectrally bright and red terrains that we call facula. The pits, and these are formed by explosive eruption. The pits can are up to several kilometers deep and can be 10 kilometers wide. Concerning the extension of the facula can range from 10 kilometers, such as the case of this facula in Mistral crater, which is about 30 kilometers in diameter, But the extension of facula can also reach the hundreds of kilometers in diameter. And this is the case of Natter facula, which is the brightest facula on Mercury, and it's also the largest one, with a diameter of about 250 kilometers. Where can we find the pits? So the pits of pyroclastic deposits. We can find them on the floors of the crater, such as here. You can observe here the pit on the center of the crater. We can find them on the rims of the crater. This is the pit that lies on the rim of the crater, but can also be found on the central peak of impact crater, such as in the case of Chagaraia. This pit is the vent of the explosion, and can also be found on the peak ring of impact structure. This region is the pit of our explosive eruption. But they can also be found on a fault. Here I have highlighted the fault that crosses the pit of the vent of the eruption, such as in this case and in this other case in the Glinka crater. But they can also found in the vicinity of a fault, such as in this case. This is a fault, and a vent of the pyroclastic deposit is this one. It's not located on a fault, but in the vicinity of it. Then on Mercury, we detected also 3 peculiar vents, are so-called vents with mounds. They are characterized by a central mound inside the vent. We are still investigating about these anomalous vents, and the Bepi Colombo data will probably provide us more information. But spectrally, we can observe that around the vent, we have the spectrally bright and red terrains that characterizes the facula. And this is the distribution of the pits from the work of PEGO 2021. They detected 188 pit vents, and among these, 131 are compound vents, 57 are single vents, and now I will talk about these 2 different vents. And 121 are ambiguous or unclassifiable because the data analyzed were not enough or had not a sufficient resolution to better discriminate their nature. So the single vent, as you can observe in this image on the left part, is as suggested by the word, is made of a single pit. So we have one single pit and then the facula. The compound vent, you have 3 cases. The compound vents are instead characterized by multiple pits inside the main one. And these are close to each other. These multiple pits are close to each other and are caused by subsequent eruption. In the case of Orm facula, this is a facula in the Praxiteles basin. We have the main pit, that is this larger one, and 2 younger pits in the southwestern part of the pit, produced, of course, after the formation of the main one. Then we have Ago facula, where several pits were identified and classified as A, B, C, then moving to H and I. And the youngest one are the H and I vents. So the older ones are A, B, C, and then going to the H and I, which are the youngest one, which are also spectrally different with respect to the other vents. And it seems here that these youngest vents probably excavated a material, a different, compositional different material. Then we have another case of SERP facula, where instead the different pits, where we have, moving from southern to the northern part of the vent, we have the older to youngest pits. So it seems that the subsequent eruption moving in the direction from the southern to the northern one. Then I spent few words for the red-pitted ground terrains. As said before, these have not a discernible vents, but this terrains is characterized by multiple pits, which sometimes are not distinguished, they are not discernibles. And they are probably formed by the passage of lava across the volatile rich substrate. But the analysis about these terrains is still, we have to understand in detail the formation of these terrains. And this is another case of the red-pitted terrains in the Raphael crater, where you can observe here that we cannot distinguish a unique event or a multiple or a specific event, but we have a pitted terrains. And this, you can observe here the pitted terrains here and in this part. And this is the map of the red pitted ground terrains, which are represented by the red dots. 24 pitted ground were detected on Mercury. And now I will talk about the hollows. From the map of Thomas 2014, about 445 hollows were detected, which are shown with pink dots. And in the new map of Barbara De Toffoli, 41 new hollows were observed, shown with the yellow dots. These hollows, as already said, are preferentially distributed on the equatorial latitudes and on the slope that face toward the hot poles. So the poles that receive a higher, which are more heated by the sun. And this is suggests a formation process linked to solar heating. Then these hollows are mainly found in the northern hemisphere. And as said by Valentina, they are found mainly in association with the low reflectance material. As you can observe on the map, we can mainly find the hollows in these blue and dark terrains, that is the low reflectance material, even if sometimes are also found in terrains which are spectrally redder, such as the high reflectance red plains, such as here, and intermediate terrains, such as the low blue plains. Hollows are therefore shallow depressions characterized by a flat floor and an irregular shape, and their age is characterized by a high albedo. You can better see these spectral properties on this image, where you can notice that the age of albedo, the age of hollows have a high albedo, as well as in this case. And you can notice the flat floor inside the hollows. Where we can find the hollows? They can be found on crater floors, characterized by these cyans. The hollows are characterized by these cyan colors in the enhanced coloring map. And so you can observe these on the crater floors, but also on the peak of, on the central peak of impact craters. And you can observe as the hollows are related to the low reflectance material inside the central peak, and also on the peak ring of impact craters. Also in this case, the hollows and low reflectance material host in the peak ring. But hollows are also found on the ejecta craters and on their crater rim or wall. And this is the case that joins both these two cases. In fact, hollows are both on the ejecta of this crater, but can be also found on the wall of this crater. What is the formation process of these two units? Concerning the facula, on the Earth, the pyroclastic deposits typically form after the fragmentation and the upward propulsion of magma particles, driven by the expansion of volatile species. So we have a magma rich in volatiles, which produces a pressure on the of the surface, of the upper layer of the surface, and produces an explosion of the surface. So we have the vent. So as a result, we have the vent of the explosion from where the magma erupted. And around the vent, we have the pyroclastic deposits. So the magma particles and rocks that deposits around the vent. On the Earth, the volatiles that are in the terrestrial magma and that are responsible for this eruption are water, carbon dioxide, sulfur compounds, and halogens. On Mercury, the possible volcanic gases are made of carbon and oxygen, but also sulfur and chlorine and neutron. The hypothesis of sulfur and carbon volatiles that are responsible for this eruption is supported by the results from two other instruments on MESSENGER, the X-ray spectrometer and neutron spectrometer. These two instruments observed the area of Natta-Rhys facula, the largest facula on Mercury, and observed a depletion of sulfur and carbon. So this could support the hypothesis that volatile rich in sulfur and carbon can be responsible of the eruption. Concerning the hollows, the possible process for the hollows formation is the loss of the volatile component from the parent material that is supposed to be the low reflectance material. After the exposition of this material to the surface and so to Mercury's environment. In fact, Mercury is lacks of an atmosphere that so it is exposed to space weathering processes that includes micrometeoritic bombardment and solar wind irradiations. These two processes can be responsible of the loss of volatile components by means of the vaporization process, for example, where the micrometeoritic bombardments can produce a sort of layer on the particles. And this layer can include the volatiles that can be then exposed to the surface and so are lost. Also, the solar wind irradiation can be responsible of the sputtering. This means the loss of specific atoms from the surface. So these are hypotheses, but generally the loss of the volatile component can be responsible of the hollow formation. And the volatiles responsible for these formations are suggested to be also sulfur components, sulfur, calcium sulfides, and magnesium sulfides. So both, as said, both faculae and the hollows are probably produced by the involvement with the involvement of volatiles. So volatiles are probably the responsible of these two units. In fact, hollows are found also nearby faculae, such as in the case of Tiagaraia, where we have both the vent with the pyroclastic deposits surrounding the vent, but also the hollows are on this central peak. So it suggested that the volatile responsible for the explosive volcanic eruption can also trigger the hollow formation. Let's talk about the spectral properties of these two units. The faculae are spectrally bright and with a redder spectral slope with the average, with respect to the average T-rays. And you can observe that on this image, where the red spectra are spectra of some pyroclastic deposits, and the spectrum, the black spectrum with a thicker line is the average spectrum of mercury. The red spectra of the pyroclastic deposits are brighter, so they have a higher reflectance than the mean one, and with a steeper spectral slope. You can also observe these in these are the spectra acquired by the MASCS spectrometer, and these are the spectra acquired by the MDIS camera. Also in this case, the pyroclastic deposits, that is this spectrum, are brighter with respect to the other units. For example, we can take into account the intermediate planes as the average mercury rains. These are spectrally brighter and with a redder spectral slope. Another spectral properties of faculae is a UV downturn that you can observe in this image. The spectrum has a sort of downturn for wavelengths lower than 360 nanometers. And this sort of curvature is ascribed to the to a specific absorption band, the oxygen metal charge transfer absorption band, that occurs when the oxygen is linked to a metal, such as iron, titanium, or other. And in fact, these spectral properties suggest that pyroclastic deposits are probably have a lower iron content with respect to the mercury T-rains, or are probably also made by a finer grains than the average one, that is smaller than 25 microns. Concerning hollows, these are represented by these yellow spectra in MASCS, in this image acquired by MASCS spectrometer. And these are among the brightest geologic unit of mercury, in fact, have a higher reflectance with respect to the other units, and have a bluer visible spectral slope. So their slope is almost flat and not red. We can also find on MASCS spectra strongest curvature in the visible range short towards 600 nanometers. So also here we have a curvature in the spectrum. And some spectra of hollows have a spectral feature at 630 nanometer, ascribed to the occurrence of sulfides and chlorides. All these spectral properties suggest that hollows have experienced a low degree of alteration due to space weathering, and also in this case, as pyroclastic deposits are probably made of fine-grained material. And this is as a consequence of the volatile loss, a sort of lag on the floor of hollows is formed. And this lag stops the formation of hollows, obtaining spectra which are redder and darker, more similar to the average mercury T-rays. Instead, on the edge of hollows in this area, where we can have the exposition of fresh material from mass wasting movements, the hollows can be active, can continue to produce, and so this produces a sort of widening of the hollow units. And the spectra typical of these, when the hollows are still active, are typical on the edge of hollows, is characterized by spectra which are brighter and with a stronger UV downturn. You can observe in this image an area where the spectra of hollows which are active, brighter, and with a blue visible spectral slope. Instead, when the hollow formation stops, this spectra becomes darker and with a redder spectral zone. Then the last argument I want to focus on is that the faculae can be present in a fresher aspect and a more degraded aspect. For example, the fresher faculae, which are relatively younger, are characterized by an orange color in an enhanced color image. But we have some faculae that seems to be older and more degraded, which are instead characterized by a sort of brownish color in this map. And they are supposed to be older and more degraded. And you can observe here the spectra of two faculae. These two spectra, the light red spectra, are the spectra of two fresh faculae, which are relatively brighter. Instead, the spectra of these faculae, this brownish facula, has a lower reflectance. And it is supposed that this lower reflectance is related to a mixing of the pyroclastic material with the underlying terrains, which are responsible of the loss of the spectral properties. And this is my last slide where I summarized the different units that I have talked about. And this summarizes how these units are can be distinguished in the NAS color map. The fresh faculae and the red pitted ground are represented with an orange color. The graded faculae have a brownish color, and the hollows are represented by a cyan one. Thank you for the attention. This is my last slide.